Hey guys, what's up? Eddie Aho here with KISSAnalog.com. Today we're going to do a quick video. It's going to be kind of a continuation of that introductory video. Just a few more details, just a little bit more explanation about the boost converter. And I'm going to kind of basically show three different states this guy can be in. One, when it's not running, but it's still putting out output voltage. Two is when its FET turns on, and three, when the FET turns off. So basically those three different states of operation. I think that might help give a little bit more explanation about how the inductor and how the capacitor are working during those different stages. Okay, so this will be a quick video, and thanks for watching. Okay, this is just a quick follow-up. Just try to give a little bit better explanation. I'm going to kind of show three different operations of the boost converter, okay? One is when the boost circuit is not really running yet. So you don't see the control chip or the FET in here, or the feedback, okay? This is like, hey, when you're bringing up the voltage, if the voltage doesn't come up high enough to turn on the boost converter, then the output's still going to get voltage, and basically that's this mode of operation right here. So the 12 volts, let's say it's 12 volts, you're going to have an inductor. Now when you first flip that switch on, let's say you just pop on the 12 volts, there's going to be an inrush of current, and we're back to where the inductor is going to want to choke that off, right? That inrush current goes to that inductor. It's going to build a magnetic field. It's EMF, electromagnetic force. It's counter EMF, and it's going to fight against that current, and so you'll get this ramp of current up in the inductor, okay? And then you're going to get a voltage drop across the diode, and then you're going to get current going to this capacitor. This capacitor initially is going to look like it's short, right? First it's going to look like it's short, kind of like how an inductor looks like an open. They're kind of the opposite. So the capacitor looks like it's short. You can't change the voltage instantaneously. You know, you can put current through it instantaneously, but not voltage. Kind of the opposite of the inductor. So current's going to rush in, charge up that cap, and as the cap charges up, the current will slow down. This inductor is going to keep that current from rushing in here looking like it's short. So there's going to be some kind of balance between these two guys. And then you're also going to get current into your load. And then eventually the capacitor charges up. You'll have 12 volts minus the diode drop. Let's just say the diode drops 0.7 volts. So over here you'll have, 11.3 volts. And then that's how it kind of sits. And when you've sat there for a moment, long enough to current to kind of settle out and everything, 0.7 volts, as when you've sat here for a little bit, then current is DC now. And now this inductor is not really doing anything anymore. The magnetic field's collapsed. That first initial inrush of current created a magnetic field, but then once it's stabilized, it just collapses. So basically the inductor's like it's short at this point. Now there's some DC resistance in here, so you have some DC resistance, a little small voltage drop because of that. But otherwise, that's one mode of operation. You got a capacitor out here smoothing out things, I guess, but this is kind of the boost circuit when it's not running. So that's kind of a unique part of the boost circuit, is that even when it's not running, your output still gets a load and everything's working. Okay, now let's just come over here. This page looks kind of busy, so let's just focus on this part right here for now. When you're up here, this is when the FET turns on. So now the FET turns on. Now we have our control IC and we have our FET, which is, I'm just showing as a switch. So the control IC turns it on. So this is closed right here. Okay. Current is going to go this way through this circuit. Okay, and it's just going to circulate around here. and that's the way your current's going to flow. Okay, and now when it first does that, it has to charge up through this inductor, so you're going to get this ramp. It's going to charge through the inductor. Now I drew like two circuits because basically that's what it is. This guy's kind of like it's short, but remember there's a diode in here. And that diode disconnects this circuit from this circuit. It's reverse biased because we have from over here, when the voltage, before anything happened, let's say we had 11.3 volts. Now all of a sudden this guy shorts out. So he takes right here and he shorts this. So that diode just pretty much separates the two circuits. So now you have this circuit over here. Now the capacitor has been filled up with current, and it's going to supply the load with current. Now what I've done is I've shown a couple equations here. Let's skip over all this stuff for a moment and let's just jump down to here. Now the gate opens again, so we're kind of back to this circuit. Okay, but that inductor, because we switched it on and off real fast, in this circuit we didn't have a switch, and so the boost wasn't running, so current's just constantly flowing. In this one, we turned it on and then turned it off real fast, so this inductor didn't stabilize. It had current charging up in it, and then all of a sudden we opened the FET. Well, it wants to continue flowing that current, so it's going to just let it continue going through it, and it's going to discharge. Kind of the opposite of up here. Up here the capacitor is discharging. Over here the capacitor is going to get charged back up with the inductor. Plus we have the 12 volts over here still pushing current. So, but the inductor is going to put current into the capacitor and into the load. So you're going to have current coming here, separating, and then rejoining and coming back. So those are kind of the three modes of operation. In this mode, what happened though is this voltage over here got boosted up a little bit because we had this energy charged on this inductor, and then when we open that switch, we get that kickback, that EMF that puts a higher voltage over here. Now it can't just go to some real high voltage because we have a capacitor that is going to try to absorb that energy, so it won't change voltage instantly. An inductor can change voltage instantly, but since it's connected to the capacitor, it cannot. So the capacitor is going to charge that capacitor up, just kind of like over here, or even on this first circuit. When we first turn on power, this capacitor wants to be as short and just take a bunch of current, but this inductor will not let it, so because it's going to fight that current. And then it's going to charge up, and then eventually when it goes to DC, eventually it's going to stabilize, and the capacitor is going to be kind of taken out of the circuit because the capacitor looks like an open circuit. It's kind of gone, no more current's going in it, and the inductor looks like it's short because the magnetic field's collapsed. So when you switch them on and off, that's when you can get capacitor discharging and then charging, so you get ripple current, ripple voltage on the capacitor when you're switching on and off. Otherwise everything's stabilized. And also the inductor, you got ramping up, ramping down. So current's ramping up, current's ramping down through the inductor. And on the voltage on the capacitor, it's going to be ramping up as it charges here, and then ramping down as it discharges here. So inductor and capacitor both store energy. They just kind of store it differently. So just kind of wanted to cover basically those three modes of operation so you can kind of think about that. Now these equations right here kind of describe how that works. IC or IL, current in a capacitor, it's equal to I equals C dV dt. Now this dV, that dV, I'm kind of in a habit doing it this way, but that's the same thing as the delta symbol this way. Okay, it's the change of, both of these mean change of voltage, or if you go DI equals, they're both DI. One's delta, one's D. So they both mean the same thing, change of. Okay. Sorry, so that's just a habit I have of drawing it like a D. But what I'm showing here is if the gate is turning on and off like this, if you map this up to here, and let's say this is output voltage, I said it's 12, so maybe it's only 11.3 when it first starts off because of the drop here. So maybe this is really 11.3 volts, not 12. That's the starting voltage, and then all of a sudden the gate gets turned on. So all of a sudden this circuit comes into play. When that happens, then over here the capacitor's supplying the current to the load, so it's discharging. So the voltage here is going to be dropping with that ripple. It's going to turn into ripple voltage on the capacitor, but the voltage on the capacitor is the same as on the load, right? They're in parallel. So current's coming in, voltage is dropping, and then all of a sudden we turn off the transistor. So the transistor turns off right here. And when that happens, now we have the inductor engaged, and it can supply current back here. So now that we get this current from the inductor, and it comes this way, and it charges up the cap, and it comes into the load. So I'm showing the current out here, so I call it IL. So it comes in here, but I'm showing now the voltage here. We're not sure how high it's going to go. I mean, we can do some math and all that stuff, but basically it's going to go to a higher point of voltage. But it can only go as high as this cap will let it in whatever duty cycle we had it. And what will happen, then it discharges again, but see, it only comes down to here, so it's a little bit higher than what it was, and it'll sit there and walk up the first few cycles. It'll keep on walking up until it charges this to whatever voltage the control chip is going to regulate the voltage to. Otherwise, if you didn't have the feedback, it would theoretically keep on increasing that voltage for pretty high voltage, but there is a limit to that. But the feedback coming back will change the duty cycle to control the voltage on the output of this. But it doesn't do it in one cycle. It takes a number of cycles for the voltage to kind of staircase up into the regulated voltage. Okay, so I hope this little quick explanation along with the previous introduction might give a little bit more meat, a little more explanation of how this works. The next video we'll talk more about the duty cycle and how this works. Alright, so that was a quick video. I hope that helped. The next video we're going to put out real quick here is one kind of showing the control loop, the pulse width modulation aspect, explain that, PWM, pulse width modulation, changing the pulse width, modulating the pulse width to control the output voltage. So we'll cover that next video, okay? Alright, hey, thumbs up guys. That was just a quick video. Just kind of thought I'd give a little more explanation on those aspects. I thought, looking at the three different kind of situations that the circuit can be in might be helpful. So hope it was. Thanks for watching.